보여? 그래서 그거 고정시켜 놓으면 돼. Okay, today we're going to continue the discussion about the bipolar transistor operation principles. And last time we had emitter, base, collector, and then we're supposed to have a space charge regions like this. And we have a piece of N, and then it goes the profile, something like this. And then we have N sub P, and here we have N sub P naught, and this is about 0, okay? Because we have a very low concentration of dopants at the base region. And we know that the minority carrier has to be deviated from the equilibrium value of this much by applying the voltage. We should write this over KT and free BE. Last time we set this as a thermal voltage, right? So if you make it free BE over free T, if you write in a simplified form like this, okay? And then NP naught, the equilibrium value of minority carrier is going to be something like this, right? This we know. We have discussed this about this equation and last diode, and also VBE over VT here, and then Pn naught is equal to Ni square over Nd, right? And if doping level is constant on the base, and then the Gummel number of the base is Q and Q, and area A, NA, XB, the base width. Then last time we set the electron current, emitter current, excuse me, it's going to be NA XB Q D N A Ni square, and e to the VBE over VT minus 1, okay? In this term, we neglect the e to the BC over VT is negligible due to reverse bias between base and collector, right? And we also can express this equation in terms of the gamma number QB by Q square A squared dN Ni square into the VBE over VT minus 1. So if you plot this, the IN with respect to VBE, the emitter voltage, then if you take a log IN, you're supposed to have a straight line, something like this, okay? And the intercept with the y-axis is going to be the saturation current, IS, which is this value, right? And in reality, it is deviated from this straight line at the end of this, and this enhancement of the current is just a leakage current of the bipolar transistor, right? And the slope here is about 60 millivolts per decade I current. This value is the very good values. In MOS transistor, it is very hard to get these numbers. Last time, the ideal case, we have a 60 millivolts per decade as a slope in the switching. But in a bipolar transistor, it can be easily achieved by making QV very small. In order to make a QV small, all you have to do is you make the concentration of the base as small as possible. And modern technology says we can make about 10 to the 12 per centimeter cube. This low doping is possible with the modern technology. So we can have a very good workable bipolar transistors. Now, today, the main topic of today's lecture is about the gain, okay? The current gain. In bipolar transistors, let me draw it again. Okay, we have depletion regions like this, and then here depletion regions like this, emitter, base, collector, and the distance between here to here is going to be the base current. Now, as far as the current gain is concerned, now we have three factors which will diminish the current gain. Actually, the gain itself is a ratio of collector current with respect to the base current. Okay, that is going to be called the gain. So we want to make this as small as possible. We want to make this thing as big as possible to get high gain on the transistors. All right, but we have three factors. 1, 2, 3 factors which will influence on the beta gain. The one thing is the recombination of electrons at base neutral region. right? This means when the electron is injected towards the base, this electron should pass this base by making the XB is much smaller than the diffusion length of the electron. So if we are able to make this base width much smaller than the electron lifetimes, should say, then before recombining, it is going to pass to the collector. But there should be some recombination of the electrons to be recombined at the base, so that will make the beta small, right? That is the one factor, and the other factor is hole injection into the emitter. We are injecting the electrons by forward biasing between this and the base, and this forward bias will inject the holes to the emitter as well. Okay, this forward bias not only injects electrons from the emitter to the base, but also for holes it should be injected into the emitter, so that the whole current is going to reduce the beta values. And the final factor which will decrease that gain is going to be the emitter base space charge region. Space charge region recombination. That means at this space charge region, electron and hole are going to be recombined at the space charge regions. The electrons and holes going to be combined at this space charge region. So those three factors are going to decrease the gain of the transistor, and therefore when you're manufacturing the bipolar transistors, you have to set up the process that will minimize these three factors. So let's discuss about those three in detail, okay? We assume that electric field in the emitter and base is 0. In other words, uniform doping of base, okay? And the electron current continuity equation says the electron current is going to be QA dN round X round NP. Only the diffusion current is possible. Diffusion current only, right? And dn dx square dx square d np minus np naught over tau n is going to be 0. And the general solution of this is np minus np naught equal to k1 e to the minus x over ln. This one we has done in the diode section, right? This np and np naught is nothing but this is np naught, and then the injected value at the space charge edge is going to be n sub p, and this is actually the profile of this decay of injected electrons into the base, okay? And that is the general solution of this equation. And if you put the boundary conditions for that, boundary conditions, n sub p at x equal to 0 is n sub p e to the VBE over VT. And so p at x equal to xb is going to be np naught, and then we assume it's approximately 0. And then np is going to be np naught e to the VBE over VT, and then hyperbolic sine xp minus x over ln, and hyperbolic sine of this. That is going to be the particular solution of that equation. And then if you put that thing into the equation, then you end up with the emitter current. The N sub E is electron and emitter. And then you end up with dN and P naught over ln e to the VBE over VT minus 1 cotangent hyperbolic ln over xb. And the collector current is going to be QA dN n sub P naught. It's the same, and e to the VBE over VT minus 1 cosec hyperbolic ln over xb. And the ratio of these two is going to be called alpha t. That is the base transport factor. And that is, by definition, I and C over I and E. Okay? The electrons survive to the collector, and then the electrons which has been recombined in the base, Okay, that is the basic transfer factor, and then we can have the ratios from here, and then that's going to be sec hyperbolic xb over ln if you use these two equations. And obviously, in modern bipolar technologies, xb is much less than n, so we have a very little recombination in the base of the electrons which has been injected to the base. And if you plot the x np naught over np over np naught with respect to the distance x, and let's say this is the xb, and then when xb over ln is about 0.1, xb is 10 times less than the ln, then we are supposed to have a straight line here. Okay? But when this ratio becomes 1, then it's deviated a little bit from this straight line, and then if it becomes 2, then it is going to be deviated far from the straight line here. This means that the injected electrons in the base is going to make a straight line diminishes to the values n sub np naught, which is about 0, and the straight line, if we make the xb the base width reasonably small. Okay, under the assumption that if xb is much less than ln, then the transport factor, base transport factor, is going to be approximated to these values, okay, from this equation. And then in general, xb is in 1 micron, ln is about 30 microns. So the transport factor is about 0.9994. It's very close to 1. Which means none of the electrons is really recombined in the base. Okay? And with this, we have a gain is greater than 1/1600. So this means that alpha t, the number one factor which influence the gain, is not really a matter, is trivial. The base current due to alpha t, okay, that is recombination on the base, okay, then that is a ni square xb over 2na tau n e to the VBE over VT minus 1. And wait, no, this is not that great. Okay, so this is one of the factors which ruins the value gain of the bipolar transistor, but it's not going to be serious. Now, the second term that we have discussed is the hole injection into the emitter. And then we have two situations here. If we have a long emitter, then in the emitter side we have a decay of injected holes. It's going to decay something like this, okay, to the end here. This is the emitter. But if we have a short emitter, then we're supposed to have some straight line decrease of the injected holes. It's very similar to the short base diode and long base diode case. So according to that physical dimensions, we can have the equations corresponding to that, and let's say the diffusion length of holes in the emitter is much less than the physical length of the emitter, then the solution for that injected hole current is going to be QA Ni square and D emitter, LP emitter, and DP emitter, e to the VE over VT minus 1. Okay. And then if XE is much less than the diffusion length by making the emitter short, then we have a equation dPe over n dE xP xe e to the VBE over VT minus 1. Those equations and solutions has been covered in the diode sections. And the injection efficiency of the emitter is defined by the gamma, and then that is the electron current, and the electron current plus the hole current, and then that is INE over I total. It's just a ratio of the total current. Okay, when hole is injected towards the emitter and the electrons injected toward the collector to the base, those has to be added to make a total current. Okay, and then the ratio between these two is going to be called injection efficiency of the emitter. And then we can see the gamma can be represented by XB over XE. That is the physical dimensions ratio, and that is doping of the base and the doping of the emitter. okay. And this equation is complicated, but we can set xb is larger than xn or xe greater than lp in reality. So we can assume this. Then this gamma can be simplified a little bit according to that. We want to make gamma close to 1, okay? And in order to make the gamma close to 1, then we should make the emitter doping concentration should be much greater than the base doping concentration. In other words, we have to dope very lightly for the base, okay? And then Xe as large as possible. And then Xb as small as possible. That's how we can make gamma close to 1. In modern technology, typically, gamma is close to 0.99 to 0.999, okay? Depending on the technologies. And this means the beta value approach to 100 to 1000, okay? And finally, we have to discuss about the emitter-based space charge region recombination. This at this space charge regions, emitter and base, the electron is going to be injected by the applied voltages, the forward bias applied voltages between the emitter and the base, right? And we also have injection of holes with this forward bias. So there should be some recombination at this space charge regions. Recombination at the space charge regions. That's what we are going to talk about. And in a diode, we already discussed about this, right? We know the recombination current is going to be A Ni WE over tau 0. WE is the depletion width, and then VBE over 2VT. Now the important thing here is this 2, where is it? The factor 2 here. That is important. Right? We usually do not have this 2 in front of a VT in the equations, but in this recombination, we come up with this 2 factors in front of the VT because recombination happens by the injected electrons and a hole or holes injected to the base. So this recombination is related to the hole generation and the electron generation, 2 things. The electron injection or hole injection alone, we have just VE over VT into exponential, right? But this recombination happens by those 2 factors at the same time, so that we have factors 2 there. So we summarize all those 3, summarize our discussion about the of current gain. Okay, we can say reciprocal of the current gain is going to be IB over IC, and that is IPE over INE plus INE minus INC. INE plus I recombination current INE. And this is the factor gamma, and this is transport factor alpha T, and this is the recombination current at the space charge regions. So those 3 factors has been discussed today, and this reciprocal of this is going to be NAXB dP over NDXE dN plus 2ln square over xb square plus NAXB WET 2dN Ni tau 0 e to the minus q, VBE over VT2. Okay? So if you plot the gain IC and IB, say, and you plot against the VE, this is log values, log scale, and e to the VBE over VT, we have 2 straight lines here. One is going to be this, and the other is going to be e to the VBE over 2 VT, right? That is a recombination current. And then the collector current IC is going to follow this line. That is IC going to follow this line. And then IB is going to follow along this line. At the small values is going to follow along this line. This is IB. Of course, when you have a large VE, this IV curve is going to follow in between here, but the IC is going to follow along this line. So, actually, this is what happened for the IC and IB. And then if you take the ratio of these two, then the beta value is going to follow this line. So, in this plot, we can see that, number one, the collector current is proportional to e to the VBE over VT at very wide range of voltage. Okay? And then IB is going to follow e to the VBE over VT at large VE, but IB is going to follow e to the VBE over 2VT at low level of VBE. So this means beta is going to go down at low levels, at low VBE. Okay, so from this figure, what we can see is that at the very weak input voltages, the bipolar transistor is not going to work well because the recombination at the space charge region is going to dominate. And then that recombination current is going to have a factor 2 in front of a VT here. So, for example, if you have a hearing aids, which when you get old, you need one of them, and then that hearing aids has to follow the very small signals, and so it has to be very careful not to dominate. The gain is not to be dominated by the recombination current in the space charge regions. So, for example, the hearing aid or the pacemaker, which you have to embed in the heart, those kind of medical devices has to be made carefully, not to be the total gain is not to be governed by the space charge 2 kT values here, because the signals of those special devices is very small. It has to work under the very small signal of the base emitter voltage. Okay, next week on Monday, we are going to work on the high-level signal effects on the gain. So far, we have been talking about the moderate emitter voltages. But if you have a high level input voltages to the emitter, then the discussions we have made so far is not going to properly applied. We have to have some side effects, if you like, side effects on the bipolar devices, and then that's a very important thing. So next week on Monday, we're going to have a high-level effects on the gain of bipolar transistors. Okay, have a nice weekend. I'll see you on Monday. All right.